So we were going over naming ionic compounds last time. I'm going to walk through these rules real fast. So they're further back. They're even further back than I thought they were. Okay. So when we're writing formulas for ionic compounds, again, the primary thing is that you're keeping positive charges balance out the negative charges. So they'll always add up to equal 0. And you identify ionic compounds based on the first element is going to be a metal, or it's going to be ammonium. That's the one exception. But the positive charge of the cation or the metal will balance out with the negative charge on the anion, which is going to be a nonmetal. So when you're writing those formulas, you're going to write the symbol for both of the ions, including their charges, and then you have to do this crisscross method, where you take the magnitude of the charge, so it's the number without the symbol, right, positive or negative, without the positive or negative, and make that the subscript for the other element. Right, so you swap them. So we did a bunch of examples. There's strontium chloride. And so SR, there's the 2 plus. And so we take that 2 and make it the subscript for chlorine. Take the 1 from 1 minus for chlorine and make it the subscript for the strontium. That's kind of where we were working at last time. And then if we've got, well, you can do this with polyatomic ions. We got the polyatomic ion quiz today. And then for those polyatomic ions, if we have multiples of those, put in parentheses. This is all just review, so we're just going to sort of breeze through these. If you do the crisscross method, like on this example, and you get numbers that can be, if you can simplify it, right? So they're both divisible by 3, or if they're both divisible by 2, then you simplify it. And then naming compounds is where we were at last time. So going from the symbol, from the chemical formula, to the name. Right, here we are. Ionic compounds. And this is the thing that I think makes ionic compounds tricky, is that there are some metals. Some metals that form more than one type of ion, and so we need to state what the charge of that metal cation is. So these are all the ones that form single charges, which is also the same list that I had you memorize. So if it's on the list that I had you memorize, then it's a single charge. If it's any of the transition metals other than scandium, zinc, cadmium, and silver, then it's going to have multiple charges that it can form. And so when it has multiple charges, we got to indicate that with Roman numerals. Cool. And this is where we were. So how would we name this compound? KBr. Yep. So potassium. And if you want, you can write the name of the anion out first. So bromine. And then we're changing that ending of that to IDE. So it becomes potassium bromide. And then why don't we need Roman numerals? Or do we? When would we need Roman numerals? Huh? Not when we have to balance out the charges, because these are balanced, right? Potassium forms a 1 plus charge. Bromine is 1 minus. So they're balanced. But what is it about potassium that means we don't need Roman numerals?
It can have multiple charges.
Yeah, it only forms one type of charge. So it's only ever 1 plus. So it doesn't need Roman numerals to tell us what the charge is. It's always the same charge. How about for this next one? ZN3N2. Zinc is correct. It's not going to be dinitride. So this is an ionic compound. So it is nitrogen. And then it's just changing the ending to IDE. Because based on just this, we'll zoom in over here. If we just have zinc, nitride, and then zinc is another cation that only forms one charge. It's always 2+. So the reason that we don't need to use prefixes to say how many of each of these elements there are is we know that zinc is going to be 2+. We know that nitrogen or nitride is going to be 3-. And then we figure out how many of them are going to be in this formula unit or the compound formula because their charges have to equal 0. Right, so that's where we do the crisscross. This becomes ZN3 and 2. So we took this one, yellow. The magnitude of that is over here. So the metal forms more than one type of ion. So if it's not in group 1A, 2A, 3A, and then zinc, silver, cadmium, and scandium, then you have to determine the charge on the anion first and use that to figure out what the charge of the cation is. So, for example, this is iron oxide. Iron is one of the transition metals right in the middle of the periodic table, not one of the ones that I had you memorize. So we have to figure out what the charge is for iron. So you write the anion first. What charge does oxygen form? 2-. And there's 3 2- charges. So that's an overall charge of 6-. And then there's 2 iron atoms in this formula. So what is the charge? Well, I guess let me ask this first. What charge do both of the irons have to have together? 6. 6 together. So these are going to add up to, so whatever this is plus whatever that charge is plus whatever this charge is will be 6+. So what's the charge on each of them? 3+. So for this name, it would be iron 3 oxide. Good. More examples, of course. Okay, so if we're naming the compound, PbO, first, what kind of compound is this? Ionic, molecular, or is it an acid? It is ionic, and why? It's not an acid. It doesn't start with H. Yeah, metal and a non-metal. So the first element is a metal, so it's ionic. All right, so first one's a metal. Is it a metal that forms more than one type of charge? Well, lead's kind of in a weird spot on the periodic table. But it is a metal, and it's not one of the metals I had you memorize. So lead does form multiple charges. So it's lead. And then what is our anion? Oxygen. And in the compound, it would be oxide. Okay, so if we have one oxygen, that's 2 minus. We have, yeah. All right, so the charge to balance out that 2 minus for lead would have to be 2 plus. So then it's Roman numeral 2. Okay. How about this next one? Close, very close. Copper's correct. And it's not sulfate, sulfide. Yeah, so IDE is always going to be just the element by itself. If this is sulfate, is SO4 2 minus. Okay, so we have sulfur. Sulfur has a charge of, yeah. Was that a 2? Yeah, okay. 2 what? 2 negative, 2 minus. And then we have 2 copper atoms. Copper, copper. So what is the charge on each of the coppers to balance out the 2 minus? This is 1 plus. This is copper 1 sulfide. All good? No questions? All right. It's all about balancing out the charges. So most of the polyatomic anions are oxyanions, which we have a quiz on today. And a series of oxyanions contains different numbers of oxygen atoms, and they're named systematically. It just means that we use a system to name them, which is great because then you can just memorize the rules of the system and be able to get the formulas for all the rest of them. So there's nitrate and also nitrite. So it just has 1 fewer oxygen. And we change that ATE to ITE ending. Just like Bud Light has fewer calories, if that helps you remember it. And then if there are more than 2 ions in the series, which for a lot of them there are, then we use prefixes of hypo, and meaning less than, and per, meaning more than. So hypochlorite has 2 fewer oxygens than chlorate, or 1 fewer oxygen than chlorite. And then perchlorate has 1 more oxygen. So this is why I have you memorize the base forms as ATE. All right, so this is the ATE, that's the base form for this. Adding per, which you can think of per as like a shortened hyper, right? It's more. And then hypo is like, at least in medical terms, like if you're hypoglycemic, you're low on blood sugar. Is this all feeling like review at least? We talked about it last week. So some of these polyatomic ions you've used before. Sodium hypochlorite is household bleach. Destroys color-causing molecules and kills bacteria. Probably used a lot of bleach in the last few years. Sodium bicarbonate in baking soda acts as a source of carbon dioxide. So when you're baking and you need CO2 gas, causes things to rise. Calcium carbonate in antacids, such as Tums and alkamints, neutralizes stomach acid. And then sodium nitrite is a preservative for packaged meats, which inhibits the growth of bacteria, especially those that cause botulism, which botulism is horrible. But nitrates and nitrites are really not that great to be eating. So there's usually, that's why you see in grocery stores, there's like nitrate-free, like deli meats and stuff. Should go for those. Yeah. Nitrates are also used a lot for fertilizers. Yeah.
Why is it sodium bicarbonate if it's like an ion, or if it's like a ion?
It's NaHCO3. So bicarbonate is when it has one hydrogen, and then the other one is something else. Or just bicarbonate would be HCO3 minus. Yeah. It's one of the like multiple, it's got multiple cations, which is why we haven't talked about it at all. I think it was on the nomenclature worksheet as one of the questions that you didn't have to do. Yeah. All right, so naming some polyatomic ions. What is the, well, is it ionic, molecular, or an acid? And how do we check? Mostly just the metal. The metal, yeah. The metal is the key thing here. Yeah, it's ionic because it has a metal, and then the second one's a non-metal, or in this case, a polyatomic ion, an oxyanion. And what is our metal? Manganese. And I would absolutely understand if you mix that up with magnesium, because they definitely did that a lot. Magnesium is Mg, manganese is Mn. Now, is manganese a metal that forms a single type of ion or multiple? Single charge, multiple charges? Because for one, I didn't have you memorize it, but two, it's, again, in the middle of the periodic table. It's in the transition metals, and it's not scandium, zinc, cadmium, or silver. So we're going to have to figure out what the charge is for manganese, and we're going to do that based on the anion. So what is this anion? Is it nitrate? Yeah. Very close. Nitrate is NO3 minus. And this has one fewer oxygen. Nitride would be N3 minus. Although you might have been also going for nitrite. It's nitrite. ITE. I know, there's a lot of them. So, but this is one of the oxyanions. So NO3 minus, nitrite is NO2 minus, hyponitrite is NO minus. So if you see nitrogen with an oxygen, if you see one of these, you see one of the oxyanions, again, in the quiz that I gave you, which is why I'm having you memorize them. If you see one of those elements, if you see it with an oxygen, then it's going to be the oxyanion. And then you can write down, you know, in this case, it's like, oh, nitrogen. So the base form is nitrate. It's NO3. This has one fewer oxygen. It's nitrite. All right, so nitrite is NO2 minus, and there's two of those. So what's the charge for manganese? Say 4? So if this is 4 plus, what are these two together? Well, this is a 1 minus, this is a 1 minus. So 2 minus? So this 2 is just telling us how many oxygens there are. This whole NO2 has a 1 minus charge. Huh? It's 2 minus. Yeah. Oh, the manganese. Yeah. Yeah, so the manganese is 2. 2 plus. All right, how about for this next one? The first element is a metal or non-metal? It's a metal. So it's ionic, and it's cobalt. And what's the oxyanion here? Carbonate. What charge does carbonate have? Yep, CO3 2 minus. So then the charge, what charge does cobalt have to have? 2 plus. Mm-hmm. So the key for these is to break them down, like I'm doing here, into the individual pieces, and say, look at just, when you get a compound and you have to name it, look at the first element, metal or non-metal. Make that decision. Now you're in ionic compounds. Say, okay, ionic compounds. Is my metal one that forms multiple charges or single charges? Oh, it forms multiple charges. Okay, so we need to figure out what the charge on that metal is. Write out your anion. In this case, okay, it's something with oxygen, so it's going to be a oxyanion. Now, which oxyanion is it? It's formed with, like here, carbon. So it's like, okay, carbon, the carbon oxyanions, the base form is carbonate, which is CO3, 2 minus. And then we have the base form here, so you can write down carbonate. Say, okay, carbonate has a 2 minus charge. Then we look at the how many of them we have. There's 1 carbonate. So okay, we need to cancel out a 2 minus, so that means that cobalt has to be a 2 plus. And if you can take that string of logic and literally write it out step by step on a piece of paper, and then use that as a general formula, then you know you've really got it down. And it'll help you practice it too, because as you go through those steps, if suddenly you blank on one of those steps, then you know that's where your gap is in naming compounds. But there are a lot of rules that by themselves are easy. But when you put them all together, it's really complicated. Been studying for a drone pilot's license, or a remote pilot license for drones. And there's a lot of rules, there's so many little rules, but every single one of them makes sense when you read the rule by itself. And it's when you try to put them all together on a test or something, or in this case, to just name a compound, that things get complicated. Okay, and I do think that ionic compounds are the most difficult because of that. So now we're going to get into molecular compounds. The first step in naming a molecular compound is identifying it as a molecular compound. And you can do that because first one's a metal, and it's not hydrogen. Right? Last week we talked about acids. Acids start with hydrogen. So if it's a non-metal that's not hydrogen, it's going to be a molecular compound. And you'll have 2 or more nonmetals. So here we're just going to learn, and have already learned, how to name binary molecular compounds. It'll only ever be 2 elements, sorry. And then for each of those elements in the compound, we have to add a prefix that tells us how many of that element are in the compound. And then for that second compound, we change the ending to IDE. So this is a table of the prefixes. And mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. So here we're checking out CO2. Right? So for our first element, if the prefix is mono, you can usually drop that prefix. It's not wrong to include it necessarily, but it usually does get dropped. So CO2 would be monocarbon, meaning one carbon, di, meaning two, in this case, ox, which is the oxygen, and then we change that ending to IDE to indicate that it's part of that compound. So it's carbon dioxide. And then if a prefix ends with a vowel and the base name starts with a vowel, the first vowel is sometimes dropped. So in this compound, this is dinitrogen monoxide. So instead of monoxide, right, there'd be two O's there. And then if you wrote it with both O's, it would look like monoxide. So just kind of drop one of those. All right, so how do we know that this is a molecular compound? Aside from the fact that the previous slide was talking about naming molecular compounds. They're both nonmetals, yeah. So first element's a nonmetal, second element's also a nonmetal, and the first one's not hydrogen. So how would we name this? We're going to use prefixes. So how many nitrogens are there? Two. So the prefix is? Yep, dinitrogen. And then 4 oxygens. So we use the prefix tetra. And this is one of those situations where you drop the vowel of the prefix. So it'd be tetroxide instead of tetraoxide. I don't know if I have any rules for exactly how to do that. You kind of get a feel for it. I'm not going to mark you off if you wrote tetraoxide though, because of that. All right, how about this next one? Again, we know it's a molecular compound because both nonmetals. And the first one's not hydrogen. So this is, we have a single nitrogen, so it'd be mono, but it's the first element, so we can leave the mono off. So it's just nitrogen. And then how many hydrogens? 3. So it's prefix, like a tricycle, trihydride. Change the ending to IDE. And I know it's really, really tempting to use prefixes like this on ionic compounds, but these are only for molecular compounds, only when it's all nonmetals. And that's it for molecular compounds. That's really all there is to it. Remember the prefixes and indicate how many of each element there are with prefixes. Acids are a subclass of molecular compounds, special type of molecular compounds that form ions when they dissolve in water. Hydrogen is the first element in the formula, followed by one or more nonmetals. And we categorize these into 2 groups. We have binary acids containing only hydrogen and a nonmetal. And we have oxyacids, which contain hydrogen, a nonmetal, and then oxygen. And those oxyacids will all be based on the oxyanions that, again, I'm having you memorize. So for binary acids, you add a prefix of hydro. Then you take the base name of the nonmetal and you change the ending to IC. And then there's a space and acid. It's so hard to see. This is hydro and this is acid. And there aren't very many of these. So there's HCl, so it's hydrochloric acid, or hydrobromic acid. You can do hydrofluoric, you could do hydroiodic, and then maybe hydrosulfic acid. That's kind of it. Okay, so first up, is it a binary acid or is it an oxyacid? Binary acid, because it's hydrogen, a nonmetal, and then there's no oxygen. So binary acid. So what's going to be the first part of the name for this? It's going to be hydro. And then the name, fluoric acid. Hydrofluoric acid is nasty stuff. It dissolves glass. So you have to use special beakers made out of Teflon. And then if you splash it on your skin, it goes straight for your bones and starts to replace calcium and causes excruciating pain. So I'm glad I never had to work with it. I've had to work with other stuff that was very sweaty, but this is no, not about it. Okay, another binary acid. And the binary acids all start the same. So what's the first part of this? Hydro. And then what's the base name of that nonmetal? Selenium. Well, selenium would be the base name. Selenate would be the oxyanion. I know. You're right, though. It's selenium. And it's selenic acid. Yeah. Oh, means aqueous or dissolved in water. Yeah. And that's all there is to binary acids. And then, I don't actually think I've told you this, the periodic table that I give you has the names of each of the elements on it too. So it'll be the symbol and the name of the element. So if you're struggling with the base name of what Se is, and you're like, is it selenide, is it selenate, is it selenite? You can look at the periodic table and see, oh, it's selenium, and then use that for these kinds of things. But memorizing them, at least most of them, speeds that up a lot. All right, so those binary acids. The oxyacids are acids that contain oxyanions. So found in the table of polyatomic ions. Again, which you should be memorizing. And you'll have to memorize also for the exam. There are going to be oxyanions on there. So we've talked about oxyanions. And you can see this is nitrate. Right? So nitric acid contains the nitrate ion. Sulfurous acid contains the sulfite anion, and sulfuric acid contains sulfate. And so it's identifying the portion of this, what acid or what oxyanion is that. And then the number of hydrogens that's associated with that oxyanion is the same as the charge. So if we had phosphate and we wanted to form an acid of phosphate, it would have 3 hydrogens. Because every one of those hydrogens has a 1+ charge. Phosphate has a 3- charge. So they're canceling out charges again, like ionic compounds. Ooh, didn't mean to do that. So the names of acids containing oxyanions ending in ITE take the form of the base name of the oxyanion, but you change the ITE. ITE changes to OUS, and then you add acid at the end. Yeah, changing the ending to OUS, or is that what you mean?
Yeah, no, I'm saying, yeah, this is exclusively for if it's
Oxyacids, yes.
Okay.
Right. For the binary acids, you're just changing the ending name of whatever the element is to IC.
Okay.
So, yeah, I'll show you an example actually in a second. You have to do that, otherwise they would have the same name. Your question?
I can't tell what's in the red box.
Oh, thank you. I always forget. This projector does not represent red. It's mostly black. It's fine with green and yellow, but not red. Okay. And then if we have the ending of ATE, we change that ATE to IC. So the thing I think that makes oxyacids tricky is, again, the fact that there's so many oxyanions. Did everybody get that? Everybody good? Here's just a list of oxyanions in no particular order. You can have oxyacids of things like acetate. So acetate is one of the other, what's the word I'm looking for? Is one of the other polyatomic ions. So there is the list of the oxyanions, and there are some other common polyatomic anions that I have you memorize. Acetate's one of those, and so you can add a hydrogen to that and get acetic acid. So it's following the same rules. ATE changes to IC, and also carbonic acid. All right, so first off, how can we tell that this is an oxyacid? It has oxygen, and the first element is hydrogen. So yeah, it's an oxyacid. What is the what is the base form of the nitrogen oxyanion? Nitrate, I think I heard it said. And how many oxygens does that have? 3. So that'll be NO3 minus. So here we have NO2. So what's that going to be named? Yep. Nitrite. So, all right, it's up here. We change ATE to IC. We change ITE to OUS. So the name of this acid would be nitrous acid. All right, so we change this ITE because we have nitrate. Change the ITE to OUS, nitrous acid. Notice no hydro in front. Okay. can do the same for this next one. Again, starting with hydrogen means it's an acid, and it also has another nonmetal and oxygen, so that means it's an oxyacid. What is the base form of the chlorine oxyanion? What was that? Oh, what was the name? Chlorate. And yeah, that's ClO3 minus. Cool. So that's chlorate. So we have 3 oxygens in chlorate, so this is, yep, per adds an oxygen, so this is perchlorate. And now we've got enough that we could name this. Again, ATE goes to IC, ITE goes to OUS. If there's a prefix, you just don't do anything with it. You leave it, it stays the same. So this would be perchloric acid. Put a line here to separate this. So if you had something like H, and this is the reason that hydro is included for binary acids and why we have to leave it off for oxyacids. Because if we have HCl, that would be hydrochloric acid. But if we had HClO3, that's just chloric acid. So the hydro is telling you this is a binary acid. And this is different from the oxyacid chloric acid, because otherwise they'd be named exactly the same. Okay. This is the best chart for naming. And the one, so for things like this, when I tried to memorize them, I would just try and redraw and fill in all the boxes from memory on a separate sheet of paper and then check it. And obviously, the first time you do that, it's going to be difficult. And the second time, you're probably still not going to get the whole thing. But trying to do the whole thing from memory and being able to like draw it out helped for me have it as a almost image in my mind, right? Because if I could draw it from memory, then it's in there somewhere, and could essentially reference it that way. And you might find ways that you can shorten it and give yourself little shortcuts. But this does cover all of the rules for all of the compounds. All right, so we've got metal, nonmetal, gives us an ionic compound, and then we've got metals that form one type of ion and metals that form more than one type of ion. And we can go down and we have the naming rules for each of those. And then if we have molecular compounds, meaning nonmetals only, then naming rules for those, which are much simpler. Or acids, where it's hydrogen and one or more nonmetals. And then that breaks down into binary or 2-element acids, and then oxyacids, which contain oxygen. And then the naming rules for those. All right, so ITE becomes OUS, an acid. ATE becomes IC plus acid. So when you're studying for nomenclature stuff, this should be your guide. This is the cheat sheet that you should use. And I did finish, and I actually just posted before this class, a whole nomenclature practice sheet. It's got 10 questions of each type, and then there's a section at the end that's mixed nomenclature questions. I didn't put acids on there, but acids also won't be on next week's test. So it'll help you with ionic compounds, single metal, multi-metal, and molecular compounds. And it has an answer key with it. But I would also try to use this first. Right, so look at the thing, try and name it without looking at anything else. Then reference this. If you still can't name it using this, or if you get a name down and you think it's good, then check the key. All right. There's one last thing, just tacked on to the end of this chapter. Oh, that wasn't it. Sorry, backtrack a little bit back into naming stuff. Another way of studying this would be to do something like this with a flowchart, where instead of writing out all of the different paths, try to write out step by step the path that you're taking for individual compounds, right? So if you're trying to name CO, say, okay, the first step is identifying it as molecular. You could draw an arrow and say, okay, add prefixes. That one's pretty simple. Other ones like this last one, well, sulfurous acid, right? So you see, okay, I have this compound, I identify it as an acid. Then I need to decide whether or not it's an oxyacid or a binary acid. It has oxygen, so I say oxyacid. Then go on to say it ends with ITE, so I need to change the ending to OUS. So multiple ways to study. Essentially, the more ways that you can get the way that you're thinking down onto a piece of paper, the better. Because it's only when you actually do that, this happened to me actually just last night. The only way you can know that you actually know something, which is a weird sentence, metacognition. The only way you can know that you know something is if you can actually put it down on a piece of paper. If you can actually externalize it in some way. Because you can run through steps in your head, but then when you go to put it down on the piece of paper, you're immediately going to be met with all of the gaps that your brain just filled in automatically. And last night there was a concept that I was trying to explain to my Chem 2 class, and I thought I had gone over the steps in my head, but I did not. So, could not actually put into words to communicate that concept. All right, this is the last thing that we got to talk about here. So, talk about formula mass. We've looked at the atomic masses of elements on the periodic table. That's that lower number. We talked about how that's calculated based on all of the isotopes that exist, stable isotopes. But for compounds, and we'll talk actually more in the next chapter why the mass there is so important. It's really like a key thing for chemistry. For compounds, though, it's a combination of all of the elements that are in the compound. So we have to add up for any compound all of the masses together, and that gives us the formula mass, or the mass of the whole compound. So it's really just the sum of the atomic masses for all of the atoms in the chemical formula. And so you take each of the, is that in the blue? That's legible. Yeah. Okay. So it's the number of atoms of the first element in the chemical formula multiplied by the atomic mass of the first element plus the number of atoms in the second element in the chemical formula multiplied by the atomic mass of the second element, and so on and so forth. So it's important to know and be able to calculate how many of each type of element there are in a compound. All right, so if we want to calculate the formula mass for dinitrogen monoxide, which is also laughing gas, the common name is nitrous. No, that's what you put in cars. So dinitrogen monoxide, laughing gas. So we have N2O. And the way I like to do this is, how many nitrogen atoms do we have? All right, so nitrogen is 2. Oxygen atoms, 1. And then we're going to multiply that 2 by the atomic mass of nitrogen. And this is where, if you're feeling extra ambitious and just go-getter, you can memorize some of these really common ones. Really just like hydrogen through like fluorine. If you memorize those, that'll help. So look at the periodic table. Nitrogen is 14.0074. For exams, 00674, I missed one. So this would be 14.00674. For exams, use the masses on the periodic table that I give you to avoid rounding errors. And then oxygen is 15.9994. Should bring a laser pointer for this. I left it at home though, because sometimes my cat is just going wild and I make him chase the laser pointer around until he's too tired to run anymore. So 14 point, or you do, right, it's 2 times 14.00674, 28.01348. And then 1 times 15.999, that's 15.9994. And then we just add those together. So it's going to be 44.01288. And the units for atomic mass and formula mass are grams per mole, MOL. Again, we'll talk about that chapter 6. Actually, we've got time. Might even talk about it now. So that's formula mass. Very often in slides, just to avoid taking up so much space, I will abbreviate these down to like 2 decimal places usually. On exams, just use the atomic masses and all the decimal places in the periodic table that I give you. That's it for formula mass. Let's actually do, briefly, one more. Let's get the formula mass for, wait, no. All right, so can anybody name this compound quickly? First element is magnesium. And then what's the oxyanion of phosphorus base form? PO4 3 minus phosphate, yeah. So this would be 2 fewer oxygens than that. So this would be magnesium hypophosphite. Now, if we want to write the formula mass for this, we need to first write down how many of each element there are. And you might be tempted to skip this step. But especially for things in parentheses, so we have magnesium, phosphorus, oxygen, it can be easy to miss the multiplication because there's 2 phosphorus molecules. So how many, or there's 2 hypophosphite molecules. How many phosphorus atoms are there? There's 2. Because there's 2 in the parentheses, you have to multiply that by everything inside. So how many oxygen atoms are there? 4. Right, because this, move up here a little bit, this PO2, this whole thing here is the same as saying PO2, PO2. That's the same thing. So that's why there's 4 oxygens, 2 phosphorus atoms. Then magnesium, that's one of the ones that I memorized. Just use 24.3, it's like a glare. Okay, use 24.31. Phosphorus is 30.97. Oxygen, you could actually just round to 16 most of the time. So 24.31. $72.93. times 16, 64. And then adding those together, oops. Oh. There we go. 198.87. I definitely would encourage you to at least write this part out like this, but you don't need to type it into your calculator one line at a time and then add those all up together at the end. You can type this into your calculator as just 3 times 24.31 plus 2 times 30.97 plus 4 times 16.00. And that should give you the correct answer also. Because your calculator will follow the proper order of operations, do the multiplications first, and then add everything together at the end. And I would also encourage you to try it this way, hit enter, get an answer, try it, put parentheses around each of the individual things, and just prove to yourself that it actually works. I do that all the time. If I'm like, oh, can I like take a shortcut here and leave some stuff out? Try it. Sometimes it works, sometimes it doesn't. But at least then, if you know the proper, like the super safe way, and then try a risky way, you can do those little tests. But yeah, prove that to yourself, because we're going to be doing this a lot. All right, so formula mass make sense? Oh, yeah.
Is the unit for that atomic mass units?
It is grams per mole, which is kind of the same as an atomic mass unit. I think numerically the same, but technically different. I haven't looked into that very much, but we're going to be using grams per mole. Okay. Another question about formula mass?